Higher education faculty are drowning in administrative overhead. Across universities, professors spend countless hours manually formatting syllabi, mapping course outcomes to accreditation standards, and entering grades into redundant spreadsheets, diverting critical energy away from teaching and research. Decades of digitization efforts and traditional software systems failed to fix this administrative bloat. Academic processes involve natural language interpretation, policy reasoning, and contextual judgment that resist rigid, rule-based coding. Resolving this bottleneck requires moving beyond isolated prompt and response chatbots. The solution lies in a structural shift to a new operational architecture known as Agentic AI. Agentic AI refers to artificial intelligence architectures capable of autonomous goal pursuit. Instead of waiting for a human to trigger every individual step, an agentic system decomposes complex objectives into executable workflows, navigates different environments independently, and iterates through tasks to achieve a final goal. Implementing this architecture shifts technology from being a passive tool that requires constant management into an independent digital teammate that actively executes the work. To understand how this functions in an academic setting, we have to look at how a user interacts with a standard generative model versus an agentic workflow. Standard generative AI operates on a linear path. A human inputs a highly specific prompt, and the model generates a single static output, completing its function immediately. Agentic AI operates as a cascading network. An initial goal triggers a multi-node sequence of autonomous actions. The system retrieves context from external databases, plans a chronological sequence, executes those actions, verifies its own work, and corrects errors before presenting the final result. This capability allows universities to adopt a model of progressive autonomy for their operations, scaling from level 0, fully manual administration, up to level 5, representing self-optimizing autonomy. Moving a specific course to level 3 or 4 conditional automation requires the underlying AI system to master 4 specific computational functions: planning, tool use, reflection, and multi-agent collaboration. Mastering these 4 functions is the only way institutions can establish effective guardrails and safely delegate complex academic judgment to software. The operational life cycle of any academic term begins with course preparation and syllabus design. To automate this, the system relies on the first agentic function, task decomposition, which is a specialized subset of planning. Unlike standard AI, an agentic planner fractures the goal of building a course folder into a chronological sequence of specific subtasks. It retrieves approved program outcomes, drafts corresponding assessment rubrics, and maps those assessments to specific levels of Bloom's taxonomy, a framework classifying learning complexity. Executing these tasks requires the second function, tool use. Instead of relying solely on static training data, agentic systems actively query external resources. The agent connects to the university curriculum database to pull prerequisites and cross-references historical student data to accurately calibrate course pacing. Automating course preparation through planning and tool use isolates the heavy lifting of document formatting and compliance mapping, freeing faculty to focus their expertise on pedagogical strategy. Once the course is built and the term begins, the focus shifts to direct student interaction and active teaching. Supporting students at scale requires the third agentic function, reflection. An agentic virtual teaching assistant utilizes reflection mechanisms to evaluate its own performance dynamically, identifying areas for improvement in how it communicates with specific learners. The operational loop of reflection happens internally. The agent generates an initial explanation of a concept, evaluates that draft against the student's specific academic profile, and revises the linguistic complexity of the text before the message is ever sent to the student. Real-world implementations demonstrate the effectiveness of this capability. Educational platforms utilizing real-time adaptive assessment and reflection reduce the time required to meet curriculum objectives, while improving student knowledge retention by 31%. Reflective AI architecture transitions online courses from static content delivery into highly personalized, responsive tutoring environments. As the term progresses, instructors encounter the high-stakes burden of the academic cycle, assessment and grading. Single large language models are structurally inadequate for automated grading. They frequently suffer from internal inconsistency and exhibit a bias toward overpraising student work. Resolving this vulnerability requires the final computational function, multi-agent collaboration. This chart shows the multi-agent scoring system. It divides the grading workload by branching the input to specialized AI personas. Subagent 1 evaluates text strictly for argumentation, logic, and evidence. Simultaneously, Subagent 2 acts as a language score, isolating grammar, mechanics, and usage. Finally, the supervisory agent synthesizes these distinct lenses. If the subagents diverge significantly, the supervisory requests multiple revised reports, producing a final score that is mathematically reliable and pedagogically sound. Moving from theoretical architecture to practical application reveals how this multi-agent system evaluates complex, handwritten examinations in real time. This image displays a live interface called ExamGPT. Vision language models, or VLMs, process non-text inputs like the scanned student coding exam shown here. VLMs are a class of AI models capable of simultaneously processing and understanding both visual images and text logic. The agent performs optical character recognition on the student's handwritten work, extracting the logic and mapping it against the course rubric. Below the score, the AI generates transparent chain-of-thought feedback, allowing the human instructor to verify the reasoning behind the suggested score. This next image shows how the system handles qualitative assessments, such as long-form essays. The top right corner features an AI plus human provenance indicator, proving the institution can track exactly how the AI assisted the grading process, ensuring transparency. This workflow exemplifies Level 3 conditional automation. The AI executes the computational heavy lifting of character recognition and rubric mapping, but the human instructor retains absolute authority to save, modify, or override the final grade. The nature of assessment shifts completely. Grading transitions from a tedious manual calculation into a high-level supervisory review, saving faculty dozens of hours per semester. Beyond individual courses, agentic systems manage institutional compliance and accreditation reporting. Traditionally, linking individual student grades to broader course learning outcomes, or CLOs, requires hours of manual spreadsheet data entry by faculty members. CLOs are the specific educational goals a student is expected to achieve by the end of a class. This dashboard shows that the agentic grading process entirely bypasses this manual aggregation phase. Because the AI graded individual exams with complete contextual awareness, performance data flows continuously and automatically into this program-level dashboard. The system autonomously flags learning outcomes that fall below target thresholds. This allows faculty to deploy targeted student interventions weeks before an accreditation visit ever occurs. Agentic AI does not exist to replace the educator. By automating the bureaucracy of preparation, tutoring, and assessment, it transforms the university into an automated operational system that protects faculty capacity for high-value teaching and research.